In this video, we're going to implement multi-class logistic regression from scratch, and we're going to use it to classify handwritten digits using the MNIST dataset, which is one of the most famous classic datasets that has been used for testing machine learning algorithms. So far, the last time we implemented multi-class logistic regression from scratch, we did it using gradient descent. But if you have a large data set, a large training data set, gradient descent can be too slow. And so what we do instead in practice is we use, instead of gradient descent, we use a variation of gradient descent, which is called stochastic gradient descent. And that's what we're going to learn how to do in this video. So let's first of all review the setup for multi-class logistic regression. We're given training data. Our training data consists of a list of feature vectors x1, x2, ... xn. Each of these feature vectors belongs to Rd, and we have corresponding one-hot encoded label vectors, y1, y2, ... yn. Each of these one-hot encoded label vectors belongs to Rk, where k is the number of classes. So if we're doing handwritten digit recognition, we have 10 classes because there's 10 digits. So k is going to be 10 in that example. And what is our objective function? What's our goal? Our goal is to find vectors beta 1 through beta k. Each of these vectors belongs to Rd plus 1, such that for each example in our training data set, if we compute a probability vector as follows, so we're going to do xiHat transpose beta 1, xiHat transpose beta 2, ... xiHat transpose beta k. Well, we're going to compute these k dot products, and then we're going to take the resulting vector and plug it into the softmax function. Remember, the softmax function is useful in machine learning because it converts a vector into a probability vector. What we hope is that this probability vector computed like this should agree with the ground truth probability vector yi. It should agree closely with this ground truth probability vector. And let's call this probability vector Q sub I. Q sub I is our predicted probability vector. We hope that our predicted probability vector agrees closely with the ground truth probability vector. And how do we measure the agreement between two probability vectors? We use the cross entropy loss function. So we compute L of yi comma qi, and this cross entropy we hope is very small. If it's small, then that means that this predicted probability vector agrees closely with the ground truth probability vector yi. And we hope that this is true for all the examples in our training data set. So we're going to sum this we're going to do a sum from I equals 1 to n. So we're looking at all the examples in our training data set, and we hope for each example, this cross entropy is small. We hope that for each training example, our predicted probability agrees closely with the ground truth probability. This function is called L of beta. This is our cost function. And when we train our logistic regression model, the way we do it is we select the vector beta that minimizes this cost function. You can think of, and what is this vector beta here? This beta is the column vector that you get by vertically concatenating these vectors beta 1, beta 2 through beta k. If you take beta 1, which is a vector, and stack it on top of beta 2, which is a vector, and so on, what you get is a big, tall column vector, and we're calling that column vector beta. And all of the coefficients in this list of coefficients here, you can think of all these coefficients as being little knobs that we can tune. And we tune these knobs in order to make the accuracy, in order to make our predicted probability vectors as accurate as possible. In other words, we tune these knobs to make our predicted probability vectors agree as closely as possible with the ground truth probability vectors. And the way we tune these knobs, we tune these knobs using either gradient descent, we minimize L of beta using gradient descent, or today we're going to use some stochastic gradient descent, which is similar to it's similar to gradient descent, but it's more efficient. It will converge to a solution much faster. In practice, it will be much faster than gradient descent. By the way, what does the word stochastic mean? All it means is having to do with randomness. So the word stochastic sounds very fancy, but it's not actually very fancy. It just means involving randomness. Okay. Let me write down our objective function one more time. L of beta is equal to the sum from I equals 1 to n of L of yi comma qi. That's our objective function. And sometimes people put a 1 over n right here. And that way it's like we're taking the average of all these cross entropy values. It's like we're computing the average cross entropy over all the examples in our training data set. That's okay. So this is what we're actually going to use as our objective function today. And so how do we minimize L? If we were going to use gradient descent, the key step in gradient descent is to compute the gradient of L. And the gradient of L is equal to, here we're going to have the sum 1 over n, and then we're going to have the sum from I equals 1 to n. And then we're going to have to take the gradient of this function, which I'm going to call this function L sub I of beta. Remember, Qi depends on beta. I haven't written that dependence explicitly, but Qi is a function of beta. So this term here, the ith term in the sum, I'm going to call it L sub I of beta. And then the gradient of L at beta is equal to 1 over n times the sum from I equals 1 to n of the gradient of L sub I at beta. Okay. And here's what you should notice right now. In order to compute this gradient, the gradient of L, we have to evaluate this big sum. And that might actually be very expensive, because if we have a large training data set, then n might be very large. N could be 1 million. And then we're taking a sum of 1 million terms. And that is a very expensive, time-consuming calculation. When we work with the MNIST data set, n is going to be 60,000. And that means we're going to have to take a sum of 60,000 terms. And we're going to have to compute the gradient of L sub I for 60,000 different values of I. And that is very expensive. That's what makes gradient descent sort of slow for training our logistic regression model. So what can we do about that? If it's too expensive to compute the gradient of L, because we have to compute a sum of, you know, 1,000,000 of these terms. If it's too expensive to do that, what should we do? Well, there's another strategy, which is called stochastic gradient descent. It's abbreviated SGD. And what you do in stochastic gradient descent is you, instead of computing the full gradient, and instead of doing the gradient descent update, which, as we know, is the updated value of our beta vector is equal to the current value of our beta vector minus the learning rate times the gradient of L evaluated at the current value of beta. This is the standard gradient descent update. So we're not going to do that. Instead, what we're going to do instead is we're going to, instead of using the full gradient, we're going to use just the gradient of L sub I at beta t instead. That's all. And you can think of the gradient of L sub I at beta t as being like kind of like a noisy approximation to the true gradient. What we really, you know, ideally, if we had unlimited computational power, we would just compute the full gradient. But instead, we're just going to compute the gradient of L sub I at beta, and we're going to view this as being like a noisy approximation to this gradient. And so our stochastic gradient descent update is going to look like this. The updated value of beta is equal to the current value of beta minus the learning rate times the gradient of L sub I at beta t. So this is our stochastic gradient descent update. Now, by the way, technically I should say that what we're doing here is stochastic gradient descent with a batch size of 1. You could, so it's like, instead of looking at this full sum of 1,000,000 terms, I am just computing this full sum of 1,000,000 terms. I'm just computing the gradient of 1 term in the sum, and I'm using that as an approximation to the gradient, to the full gradient. Well, you could also, the batch size doesn't have to be 1. Here's something else I could do if I wanted to get a little bit more fancy. I could use like 32 of the terms in this sum selected at random, and I could compute a gradient based on those 32 terms in the sum selected at random, and whatever that gradient turns out to be, I could use it here. But for simplicity, we're just going to use a batch size of 1. So this is our stochastic gradient descent algorithm. That's what we're going to use. That's what we're going to implement today. And by the way, let me say a little bit more about this. So when we do this beta update here, which value of I do I use? Well, we just choose I at random, just at random. That's why it's called stochastic. That's why it involves randomness. The value of I is chosen at random. So we select a value of I at random, we update beta using this formula, then we select another value of I at random, and we update beta again using this formula. Then we select another value of I at random, then we update beta again, and we just keep doing this. And that's how stochastic gradient descent works. Now, one more comment. When I select the next value of I at random, should I select sort of with replacement or without replacement? In other words, do I allow for the possibility that the next value of I choose happens to be equal to the previous value of I? Should that be allowable? Or should I select randomly without replacement? That means the next value of I that I choose is not allowed to be equal to the previous value of I. In practice, it tends to be better to select without replacement. So here's another way to summarize what we do in stochastic gradient descent. We're going to select a value of I at random, update beta, and then we're going to select a different value of I at random and update beta, and so on. Each time selecting I at random, but it has to be a different value of I than one of the values of I we've already selected before. And then we keep doing that until we have swept through the entire training data set. And once we have finished sweeping through the entire training data set, that's called one epoch. So there's this word epoch. If you read about neural networks and training neural networks, they use stochastic gradient descent, and they're always talking about how many epochs do I use? Do we use 5 epochs? Do we use 10 epochs? And so now we know the definition of an epoch. It's just one sweep through the training data set. One full sweep through the training data set. That's called one epoch. And typically, how many epochs do we do? Maybe 5, maybe 10, maybe 50. It depends. But so now you know how stochastic gradient descent works. And this is what we're going to implement. So let's recall, what is the formula for the gradient of L sub I at beta? Well, we figured this out, and we have a worksheet where we work this out in detail. And the answer is that, so you know how beta is a column vector, and we wrote beta using block notation. The first block of beta is the vector beta 1. The second block of beta is the vector beta 2, and so on. The final block of beta is the vector beta k. Well, the gradient of L sub I has exactly the same shape as beta, exactly the same shape. It has exactly the same block structure. And what are the blocks of this vector? Well, the first block is q sub I1 minus y sub I1 multiplied by xiHat. Here we have the first component of qi subtracted and then minus the first component of yi. The second block, and then we're multiplying by this column vector, xiHat. It's an augmented feature vector. Okay, that's the first block of this gradient vector. The second block is qi2 minus yi2 times xiHat. Okay, and you see the pattern now. The final block is going to be qik minus yik times xiHat. This is our formula for the gradient of L sub I, and this is what we derived in a worksheet that is posted on Canvas. So, knowing this formula for the gradient, we are ready to implement gradient descent. Now, I mean, we're ready to implement stochastic gradient descent to train our logistic regression model. let me make one comment about what we're going to do when inside the code in order to make the coding a little bit easier. So here I said that beta is a big, tall column vector, and it would certainly be possible in the code to store beta as a big, tall column vector. We could do that, but it actually turns out to be a little bit easier in the code to store beta as a matrix. And the first row of this matrix is beta 1, but as a row vector. I put a transpose here to make beta 1 into a row vector. And the second row is beta 2, but as a row vector, and so on. The final row of this matrix is beta k, but as a row vector. So inside the code, it's gonna be more convenient in the code to store beta as this matrix instead of as a column vector. But remember, conceptually, beta is just a column vector. And now, what about this big column vector here? It has exactly the same shape as beta. It has the same number of blocks. We're also going to store this as a column vector, as a matrix, just like we're storing beta as a matrix in the code. We're also going to store this vector as a matrix in the code, because that's going to make the code a little bit easier to write. And so this, instead of storing this as a vector, I'm going to store it in the code as a matrix that looks like this. The first row is going to be qi1 minus yi1 times xiHat transpose. That's the first row. The second row, that's the first block. The second row is qi2 minus yi2 times xiHat transpose. So we're just taking the second block of this big vector and we're just storing it in the second row of this matrix. And so on. The final row is going to be qik minus yik times xiHat transpose. Okay. Now, this is our, so we're going to, this gradient vector, we're going to store it, instead of as a big tall column vector, we're going to store it as a matrix like this. And here's one little tip, here's one little clever thing that's going to make it easier to compute this matrix in Python, and it's going to help us compute this matrix quickly in Python. I want to recognize that mathematically, this matrix, mathematically, is equal to q sub I minus y sub I multiplied by xiHat transpose. So let's look at what's happening here. Here we have a k by 1 column vector. And here, because of the transpose, we have a 1 by k row vector. So we're doing k by 1 multiplied by 1 by k. The result is a k by k matrix. The result is this matrix, which is k by k. If you don't believe that this is equal to this, just work it out on paper. You can easily check that this gives you the same answer. And so look how nice this is. The gradient of L sub I at beta in our code can be computed just with this little operation right here. We just have to multiply this times this, and then we've got it. The gradient of L sub I at beta, in our code, we compute it just using this command, that's all, just by computing this quantity. That's going to make it easier to write our code, and it's going to make our code faster. Okay, now let's actually write the code. So the first thing that I want to do is just read in the MNIST data set. And I'm going to use, here I'm importing TensorFlow. The only reason I'm importing TensorFlow right now is because TensorFlow makes it very easy to read in the MNIST data set. So let's run this code. And so what I have here, let's look at this. X train dot shape. We have 60,000 training examples, and each training example is a 28 by 28 image. And let's look at the first training example. So let's look at X train of 0. That's the first training example. Let's do image.shape. So this first training example is a 28 by 28 image. And let's import matplotlib.pyplot so that we can look at our image. So we're gonna, okay, now let's look at this image. There, it's a handwritten digit. It looks like a 5 to me, maybe. It's actually kind of hard to read what that says, but I think it's a 5. And let's look at X train of 1. That's a 0. And then let's look at the second training example. That's a 4. And then there we've got, that looks like a 9. And maybe a 2. And a 1. So this is the training data we're working with. And we're trying to develop an algorithm that can automatically classify these handwritten digits. Historically, this was a very hard problem. And it took a long time until we discovered machine learning algorithms that were able to solve this really well. Okay, so we have read in the training data. Now, I have also sort of normalized the training data. I divided by 255. The reason to do this is so that the intensity values of all of our images are always going to be between 0 and 1. And that is going to prevent us from having overflow errors inside our code. Like the code will somehow just be a little bit more stable. We won't have as much danger of overflow if we normalize the data like this. Okay. Now, what do we need to do to implement logistic regression? So let's do a few chores. We have to implement the softmax function. So the softmax function takes a vector u as input, and then let's compute. I better import numpy. And the softmax function, it works like this. We apply the exponential function to each component of u, and then we take that vector and we divide by the sum of all these exponential functions, or the sum of all these terms, and that's it. That's what the softmax function does. So we have just implemented the softmax function. Let's also implement the cross entropy loss function. So cross entropy, it's going to take a probability vector p and another probability vector q as input, and it's going to return minus the dot product of p with the log. We're going to apply the logarithm function, the natural log function, to each component of q, and we're taking a dot product with p, and then that's it. That one single line that we have right there, that's the cross entropy loss function. Okay. Now, we're going to use stochastic gradient descent. So let's decide how many epochs we should use. And let's start with 5 epochs. And let's just see how that goes. Okay, now we also need a learning rate. So let's try 0.001. Let's try that. Okay. Now we need to, let's actually, you know what? We should make a function. We should make a function that does multi-class logistic regression. So let's put all this inside a function. So let's say, what should we call our function? Let's call it log reg. And the function is going to take as input the feature vectors and the labels, and it'll take, let's say it takes the learning rate alpha also as input. Okay. Inside this function, we're going to set the number of epochs equal to 5. Let's just see if our code runs so far. The code does run. That's a good sign. Okay, the number of epochs inside this function is set equal to 5. Let's call this function logreg SGD because we're going to use stochastic gradient descent. Okay, we have to initialize beta. So let's initialize beta to be all zeros. And what's the shape of beta? Remember, we're storing beta as a matrix, as we discussed, and it's a matrix that has k rows and it has d plus 1 columns. And I better get the value of d. So let's do n comma d is equal to x dot shape. I also have to remember to augment my feature vectors. That's important. It's easy to forget augmenting the feature vectors, but we have to do that. So I'm going to do x equals np dot insert of x and then 0 and then 1 and then axis equals 1. This numpy command here augments the feature vectors in one single line. That's all you have to do. Now our feature vectors are augmented. Let's just run this and print x dot shape. Well, let's not run it yet. We're not quite ready to run this yet. Okay. Now, we have, where are we? We have initialized beta. Good, we initialized beta. Now we want to do stochastic gradient descent, and we're going to do 5 epochs. So let's have a for loop for EP and range of num epochs. And now in each epoch, we're going to sweep through the training data in random order. So let's randomly shuffle the training data. So let's create a permutation. We'll do PRM, stands for permutation. It's equal to np.random.permutation of, and then n, because n is the number of examples in our training data. So just to illustrate this, if I do np.random.permutation of 5, that's what I get. I get a random shuffling of the indices from 0 to 4. So we have now randomly shuffled the training data. And now let's have a for loop that does this for I in perm. So now we're going to visit each, in this for loop, we're visiting each training example, but in a randomized order. Okay, now let's get xiHat. xiHat is going to be the ith row of x. So I'll just do x of I. That gives me the ith row of x. Let's do yi. Yi is going to be the ith row of y. Okay. And now let's make our predicted probability vector. So I have to do, I have to compute a bunch of dot products. And I can do all those dot products at once in a clever way. Here's a clever little thing. I'm going to do beta at xiHat. And when I do this, we're multiplying the matrix beta by the vector xiHat. And what happens when we multiply this matrix by this vector? Well, we do the first row of the matrix, which is beta 1, dot product with this vector. And then we do the second row of this matrix, which is beta 2, dot product with this vector, and so on. So this command does all k dot products at once. And then the resulting vector, I'm going to plug into the softmax function. So we have just computed our predicted probability vector right there in that one line. Now we need to compare. Oh, so what do we need to do now? Now we need to compute the gradient of L sub I. So let's call it grad sub I. And remember, grad sub I was equal to the column vector Qi minus Yi, and then multiplied by the row vector xiHat transpose. That's what we discussed earlier. That's the slick way to compute the gradient of L sub I. Let me call it the gradient of L sub I. Now, that type of linear algebra computation where you multiply a column vector by a row vector, which is what we're doing right now, that type of product is called an outer product. And NumPy will do it for us. If I do numpy.linalg.outer, and then of Qi minus Yi, comma, xiHat. There. NumPy computes that outer product for us using this command. Good. So we have now computed the gradient of L sub I. There it is. Okay. And now that we did that, we're ready to update beta. So let's do beta equals beta minus alpha, the learning rate, times the gradient of L sub I. That's our stochastic gradient descent iteration. There it is. And that's it. Okay. Now, we're going to want to be able to measure our progress. Are we making progress? As the stochastic gradient descent iteration proceeds, are we making progress? And how do we measure if we're making progress? The value of L, our cost function, should be being reduced. So let's make a function that computes L. I'll call it eval L, and it's going to take our training feature vectors, and it's going to, as input, and it's going to take the labels, and it's going to take beta, our current estimate of beta, as input, and we have to compute the value of L. So let's do n comma, let's do n equals x dot shape of 0. That's the number of training examples. And then let's have a big for loop. That in this for loop, we visit each of our training examples one at a time. And now let's look at the ith feature vector. Let's assume that x is already augmented. Assume feature vectors are augmented already. So this xi, let me call it xiHat because it's augmented already by assumption. And let's look at the corresponding one-hot encoded label vector, which is y of I. Let's make our predicted probability, which, as we did previously, we compute our predicted probability vector like this. And now let's, up here, I should have initialized L to 0. And then let's see how well our predicted probability vector compares with our ground truth probability vector. And we use the cross entropy loss function to do that comparison. And then that is our that's our loss for the ith training example. Okay, so that's it. And then let's just return L. And there we have a function that evaluates the cost function L. Okay, good. Now let's return back, let's go back to our stochastic gradient descent code. And right here, we have just completed one epoch. Actually, let's do this at the beginning of the epoch. We're about to begin one epoch of gradient descent, of stochastic gradient descent. Let's go ahead and evaluate L. So let's do L equals eval L of x y beta, and let's store that value. I want to store that value. So let's create a list that's called lvals, and this list is initially empty. And let's store this value. So I'll just append L to that list. Okay. Now, if things are working correctly, these cost function values should be decreasing because we're trying to minimize L. So they should be decreasing if things are working correctly. And let's actually, let's print out, let's do a print statement to just report on the progress. So let's report what's the current epoch. And then let's report also the current cost function value. There. That'll just report on our progress. Okay, so we have implemented stochastic gradient descent. And now let's actually use it. Okay, so up above, I just read in the training data. At this point in the code, I read in the training data. And let's do, let's reshape the training data so that each image, each 28 by 28 image of a digit, we're gonna store it as just a long vector. So let's do ntrain x train, no, wrong, ntrain, and then num rows, and then num calls is equal to x train dot shape. And then let's do x train equals np dot reshape of x train. And the new shape is going to be, it's going to have n rows, and then the number of columns is going to be num rows times num calls. So basically each image of a digit, which had, each image was originally 28 by 28, now each image has been reshaped into just a vector with 28 squared entries. That's what we just did. Okay. Now, let's look at Y-train. That's the shape. We have 60,000 labels. And let's look at the first 10 labels. So each label is a number from 0 to 9 because we're classifying digits. But we need to use one-hot encoded label vectors. And we can get those using pandas. So let's import pandas as PD. Now, let's do ytrain equals pd.get dummies of ytrain. Let's just try this at the console and make sure that works. So at the console, let me do let's just do this, y equals pd.get dummies of ytrain. Let's try that. And now let's look at y.shape. So it's 60,000 rows and 10 columns. And let's look at the first 5 rows. So you can see that we have performed one-hot encoding. Oh, I forgot. Let's look at the type of y. It's currently a pandas data frame. I would prefer that y is just a NumPy array. So I can do that by putting dot values here. So once I do this command, the type of ytrain is now, it's now a NumPy array. Its shape is 60,000 rows and 10 columns. And let's look at the first 5 rows. There it is. There's our one-hot encoded label vectors for the training data. Okay. Now, here, okay, so we're ready to do stochastic gradient descent. Let's decide on our learning rate. It'll be 0.001 for starters. And then let's try 0.01, actually. And now let's just call our function. So let's do beta equals log reg SGD of x train, comma, y train, comma, alpha. And in our stochastic gradient descent function, oh, I forgot to have a return statement. That's important. I need to return beta. And let me also return L-vals, because we're going to want to look at L-vals and see what they are. Up here, when I call my function logreg SGD, let's also get L-vals as output so we can look at them. Okay. Now, all my functions are defined down here. I think before I call this function, I think I have to call the function after those functions are defined. So I'm gonna take these lines of code and I'm gonna do all this down at the bottom after my functions are defined. So I'm gonna do all this down at the end there. Okay. And then once it's all over, let's do a semi-log y plot of L-vals, and then we're gonna check and make sure that the cost function values really are decreasing. That's how we're gonna know whether or not our algorithm is working. Okay. Now, I just wrote all this code and I haven't been testing it as I go along, so there's probably some bugs. So let's run this first in debug mode and let's just see how well it works. Okay, so I'm gonna step through the code one line at a time. All right, we just read in the training data. We just normalized the training data and the test data. And let's see, we're having trouble on this line. Cannot reshape. Let's try to see what went wrong there. What is xtrain.shape? 28 by 28. What's n? N is wrong. N is supposed to be 60,000. Where did I get that n from? Oh, I see. Here I was supposed to do n train. That's 60,000. N train is 60,000. Okay, that's one bug down. Let's try it again. I'm going to run the code again in debug mode. Continue. Okay. So I just reshaped X train. Let's look at the shape of X train. 60,000 rows, 784 columns. And why is it 784? Because 28 squared is 784. And each image in our data set is 28 by 28. In other words, 784 numbers. Okay. And let's look at ytrain.shape. That's good. There's our learning rate. And now I want to step into my function. So we're stepping inside our stochastic gradient descent function. Let's look at n, 60,000, that's good. D is 784, that's good. Let's look at x.shape. That's good. Why is it 785? That's because we already augmented the feature vectors. All right. Oh, I'm referring to k, but I don't have k yet. So I need to put a line here that says k is equal to y.shape of 1. That's the number of classes. Okay. Let's start over. I'll put a breakpoint here. I'll remove this breakpoint. Remove this breakpoint. Run the code in debug mode. Here we are. Step through. Now, what's the value of k? It's 10. We have just initialized beta. Okay, beta has the correct shape. Now we're doing the first epoch of gradient descent. And let's look at eval. Let's step into eval L. Step into. Okay. Now, N is 60,000. We're looking at each training example one by one. We're looking at xi. We're looking at the ith feature vector. That's good. There's our ith training, our ith label vector. Notice it's one hot encoded. Now we make our prediction. There's our predicted probability vector. And then we compare, and let's see what L is right now. Okay, there's L. So that's good. That seems to be working correctly. Let me put a breakpoint in here. And let me just continue until we get to that point. Continue. Okay. So let's print. There's L vowels right there. All right. Now, we're on the first epoch of stochastic gradient descent. We're about to sweep through the training data in a randomized order. So let's look at this PRM. What is PRM? What's its type? It's a NumPy array. What's the shape of PRM? 60,000. And let's look at the first 10 entries. So what we've just done is we're just looking, we've just got the training examples. We've got the indices from 0 to 60,000 in a random order. That's all. And now we're just going to sweep through the training data in a random order. So here is now we're looking at one of the feature vectors selected at random. And here's the corresponding label vector. We're going to make our predicted probability vector. There it is. And now we're going to compute the gradient of L sub I. So there's apparently no outer function. Oh, I don't think I was supposed to do linalg here. I think it's just np.outer. I think that's it. Okay, so let's start over here. Okay, I'm gonna run the code again in debug mode. Continue to the next breakpoint. Okay, now we're ready to compute the gradient of L sub I. Let's see if this works. Okay. Let's look at the shape of grad L sub I. Good, that is the correct shape. Okay, now we're ready to update beta. There, we did it. We updated beta. Okay, so it seems like things are working. I mean, I don't see an error so far. We'll see if it actually works. So now let's quit, and then let's actually just run the code and see what we get. All right, so I'm just gonna run the code. Okay, so it's running. So, okay, the objective function value decreased substantially. Okay, it decreased again. Decreased again, we're making progress. We're reducing the value of L. That's good. Still reducing the value of L. Good. All right, it appears to have worked. We did it. We used stochastic gradient descent to minimize L. Okay. Now, we're ready to make our predictions. Let's make a new function that's called predict labels. And it's going to take as input a list of feature vectors and beta. And it's going to make predictions for each of the feature vectors. Okay, so let's, what's the first thing we have to do? we have to augment the feature vectors. So let's do x equals np.insert of x, 0, 1, axis equals 1. That special line augments the feature vectors. And now, let's do n comma, let's do n equals x dot shape of 0. That's the number of feature vectors that we're looking at. This is the number of feature vectors in our test data set now. And now let's have a for loop for I in range of n. And let's look at the ith feature vector. And let's make our predicted probability vector. Okay. And now let's make our prediction. K is equal to, this Qi is a list of probabilities. And what's our predicted class? Let's do K is equal to np.argmax of Qi. That's our predicted class. And now, let's store our predictions. Predictions will be equal initially to an empty list. And then let's do predictions.append of K. Okay, so we've got our predictions. And then let's just return our predictions. There. That's our function that predicts the labels for the data in our training data set. Okay. So now, let's make our predictions. So let's make our predictions on X test. So let's do predictions equals predict labels of X test, comma, beta. And I think I need to reshape X test first. Currently, that's the shape of X test. So I need to reshape it before I can make my predictions. So I'll do X test equals np.reshape of, and then X test, and n test is, that's the number of test examples in our data set. So that's X test.shape of 0. Okay, there. So we have just reshaped X test. And now, good. So now we're ready to make our predictions. Should we just try it? Let me just run this section of code and just see if it works. Okay. Oh, here, this was supposed to be n test. Let me just run. Let me run all the code again. I'm running the code again. We see we're having this nice reduction in the objective function value. That's nice. Seems like it's working. That's good. And okay, now let's try, let's see. Not sure what's happening here. Okay. Let's look at lvals. That's good. That's what we wanted. Now, let's try. Let's compute n test. So now what's the value of n test? 10,000, that makes sense because in the MNIST data set, we're given 10,000 test images, 60,000 training images, 10,000 test images. Okay, let me try out this line at the command line, at the console. Let me do check equals this, and then check.shape. That looks good. Okay, I'm ready to run this line. Okay, now let me compute my predictions. Okay, we just computed our predictions. And how many predictions do we have? 10,000, of course. Let's look at the first 10 predictions. Good. Okay. Let's look at the first 10 ground truth values. Okay, that looks pretty decent right there. Because our first, look at the agreement. We predicted 7 and it was a 7. We predicted 2, it was a 2. And 1, 0, so 1, 1, 0, 0, 4, 4, 1, 1, 4, 4, 9, 9, 6, 5. We made an error there, 9, 9, but we got the rest right. Pretty good. Okay. And let's compute our accuracy. So let's do let's say for I, let's set num correct equal to 0, and then for I in range of num test, we're going to do if predictions of I equals y test of I, then num correct is increased by 1, and then our accuracy is equal to num correct divided by num test, and then let's print our accuracy. Okay, so we're just printing the accuracy. Good. Oh, num test is not defined. That's because I've been calling it in test, not num test, it's in test. All right, so we just got 92% accuracy on the MNIST data set using logistic regression. And that's as good as you can do with logistic regression on the MNIST data set. 92% accuracy, that's it. So it worked. Now, one final thing. Let's modify our prediction function to return not just the predictions, but also the probabilities. So here, K is our predicted class, but let's also compute the probability, which I'll call Q. Let's do probabilities dot append of np dot max of qi. Okay, and then let's return probabilities as well as predictions. Okay, so then let's do predictions and probabilities. Okay. So let me, so we're returning, what we're getting now is not just the predictions, but also how confident are we in each prediction? How confident are we? And I would like to look at the predictions that we got wrong, but where we were still very confident. So let's try to do that. So let's do agreement equals, and then predictions predictions equals X equals Y test. Let's compute this. What is this thing? What we have here is a NumPy array, and let's look at the shape of this thing. 10,000 entries. Let's look at the first 10 entries. Okay, true, true, true. There's a false here, true. This just tells us whether or not our prediction was correct. Was our prediction correct or was it not correct? That's all it tells us. Okay. Now, let's do sorted indices. Let's sort the arg sort. Let's sort our probabilities. And then this function sorts in ascending order, but I want these indices in descending order. So let's do sorted indices equals sorted indices of colon, colon, -1. I just reversed the order. Okay, so let's see what we have here. Probabilities. Oh, I have to rerun this. Rerun the code. Just wait for this to run. And then what I'm going to want to do is I want to look at the predictions where we were confident but also wrong. And I want to try to see what went wrong. Why did we get fooled? Okay. N test, X test, predictions. Okay. Now what is sorted indices? It's a NumPy array. Its shape is 10,000. Let's look at the first 10 of them. Okay, it's just a list of indices. And let's look at probabilities at these particular indices. Let's do, what is probabilities again? Probabilities is a list. And then let's make it into a NumPy array. Probabilities equals np.array of probabilities. And then let's try this again. Probabilities of sorted indices of 0 through 5. Okay, look how large those are. These are the test examples where we are most confident. And let's look at the final 5. Let's look at the ones where we're least confident. Look how small those are. These are the test examples where we are least confident. Okay. Now, let's do for I in sorted indices. If agreement of I is false, that means that we failed to classify this image correctly. Then, what I want to do is look at, so x of I want to look at this image. So let's do xi equals x test of I. What's the shape of x test at this point? Okay, good. And then I want to reshape it into an image. So I'm going to reshape this xi so that it is an image with 28 rows and 28 columns. And then, well, actually, let me do something a little bit simpler. Let me just print I. I'm just going to print I. There we go. This is our list of I's. And at the top of this list, actually, let me store these I values in a list. So let me do difficult examples. Let's make it first an empty list, and then let's add I to the list. Difficult examples dot append of I. Okay, let's try this. Okay, so let's look at the length of difficult examples. 773, that's good. Let's look at the first 5 difficult examples. There they are. These are the ones where we failed hard. We were confident, but we failed. So what's probabilities of difficult examples of 0 through 5? Look how confident we were. 99.9% confident, and yet we failed. We got it wrong. So let's see what was our, let's take a look at this first difficult example. So let's say I equals difficult examples of 0. And then let's do xi equals x test of I. And let's reshape it to be 28 by 28. And then let's look at this thing. Let's look at this image. There it is. And look how confusing this image is. Now you can see why we messed it up. Because what is that? As a human, I would guess that's a 2. But that's very hard for a computer to figure out. So let's look at what was our prediction. We predicted it was a 4. That's not crazy because there's this vertical bar here. Kind of looks like a 4. This and this kind of looks like a 4. Let's see the ground truth. 2. So the ground truth is that it was a 2, but we predicted a 4. And you can see how we made that error. You can see why that example was so confusing. Let's look at another one. All right, now what is that? This is confusing. As a human, I would guess this is a 2, but it looks a lot like a 7. So what did we predict? We predicted that it was a 7, and who can blame us? Who can blame our algorithm for predicting 7? That looks a lot like a 7. And let's look at the ground truth, 2. But it looks a lot like a 7. You see that? Okay, let's look at the next one. All right, that is very confusing. And I think that I would predict that as a 7. But let's see what our algorithm predicted. Predictions of I. We predicted it was a 2. And hey, it looks like a 2. So who can blame our algorithm? It looks like a 2. The ground truth is 7. So humans are good at this. I was able to recognize that was a 7. It's tough for the algorithm to figure that out. Now, later, we'll train neural networks, convolutional neural network, and they'll be great. They'll be able to handle this. Okay. Let's look at the next. Let's keep doing this because this is kind of fun. Let's look at the next one. 3. All right, that is a messy digit. I would guess that's an 8. Our algorithm predicted it's a 4, and this horizontal line here looks like kind of like a 4, and this, it does look like a 4. And the ground truth is 8. All right, so it's interesting to look at the examples where we were very wrong and see why did the algorithm get so confused? Why was it so confident and yet so wrong? So that's interesting to look at.